More capacitance. We love it. We love capacitance. Actually, capacitance is kind of fun because it's not terribly difficult to understand, perhaps, and it's not terribly difficult to calculate. Just multiply a couple of numbers. I mentioned in the last recording the answer to the question, how much charge can you store in a capacitor, depends on how much potential difference you apply across the plates of the capacitor, in other words, how big your battery is, and also on the physical properties of the capacitor. The capital C here is a constant. I called it the capacitance, and I said that the numeric value of that thing determines the, helps determine anyway, the amount of charge that you can, the maximum amount of charge you can store in your capacitor. And I also mentioned that C depends only on the geometry, the construction of the capacitor, and not on how big a battery you attach to it, okay? Pause the recording just for a moment. Okay, sorry about that interruption. I know for you it's just been a moment. For me, it's been about half an hour since I had to pause the recording. Somebody came in that I had to talk to. So I'm not exactly sure what the last thing was I said, but in any case. So I know I was talking about the maximum charge you can store in a capacitor. It depends on the battery you attach to it and the construction of C, construction of the capacitor, which is reflected in the value of C. And so what I want to do now, and I think this is what I said, is that I want to show you an example of actually calculating C theoretically, which we almost never do, but I want to do it for you here, partly to show you that it can be done. This isn't all black box stuff. It isn't all stuff that we're going to refuse to ever show you because you can't possibly understand it. Of course you can. And I'm going to show this to you, and something else will happen as a result of having done this example. So I'm going to calculate for you the capacitance of a so-called parallel plate capacitor, which in fact I have already shown you pictures of. Okay. And so it's this. And in fact, I think I'm going to go ahead and use this diagram with some slight modifications. The first one is I'm going to take the light bulb out. And I'm going to get rid of this notation here. And then I'm going to say, okay, the plates have surface area A. Both of them have area A. Okay. Yeah. So when I talk about the area, I'm talking about when I use A in the calculations that I'm about to do. A is going to be the area of just one of the plates. We're not going to double it for two plates. A is going to be one. Okay. And which, by the way, and we'll talk about this in class as well, but when I talk about the charge that you store, remember that we transfer charge from one plate and dump it on the other plate. And so when we talk about Q, the amount of charge that we store in the capacitor, that Q refers to the magnitude of the charge that gets transferred. And so Q is essentially the magnitude of charge on just one of the plates. We don't double it and call it 2 times Q or anything else like that. Just A is the, when we talk about A, we're talking about the area of just one of the plates. When we talk about Q, we're talking about the magnitude of the charge gained or lost by just one of the plates. Okay. So the goal here is to calculate the algebraic expression that allows us to calculate the capacitance of this capacitor. All right. The strategy that I'm going to employ is to recognize that the potential difference that the battery creates and therefore ends up, once the capacitor is fully charged, the potential difference across the plate, as I've said before, is equal to the potential difference created by the battery. Okay, so when I write down V in the next expression, although it's going to be mathematically equal to the potential supplied by the battery, it's going to be conceptually referring to the potential difference across the plates. Okay? Since we have put a bunch of positive charge, since we've transferred a bunch of positive charge from the top plate to the bottom plate having gained a bunch of positive charge will have a net charge of plus Q. The top plate in direct consequence, will have a net charge of negative Q. Okay? That having happened, and now I'm going to draw you an end view here. There will be an electric field between the two plates. There's the top plate. There's the bottom plate. This is an end view now. We are attaching it to the battery. I will stay with my color coding since I've gone to all the trouble. Okay, so that's potential difference of V, and so therefore we're going to have a potential difference across here also of V. This distance here is D. And the thing I want to point out is the bottom plate has picked up an overall positive charge. The top plate has been now has an overall negative charge. And I'm going to draw the electric field now that exists between the two plates. And perhaps we've talked about this before, perhaps we haven't, but if you've seen this before, or if what I'm about to say makes perfect sense, great. If it doesn't, please just take my word for it. But the bottom line is that the field from the bottom plate being positively charged, of course, so this is plus Q down here, this is minus Q up there, and remember these plates have surface area equal to A. The electric field from the bottom plate points perpendicular, that is to say normal, to the plate, and points directly away from the positively charged plate, whereas the field of the negative plate also points perpendicular, but this time to the negative plate, but also to the positive plate as it happens, right? But it points towards the negative charge, and you'll notice that both fields point in the same direction, and so the total field ends up being nice and uniform and large. Okay, so we get a large potential difference there, and therefore a large overall electric field pointing that direction. Okay, so we have the electric potential, the electric field related to that electric potential, and the distance between them. A charge moves from high potential down to low potential since the charge moves through the field, moves through the potential difference. There's a change of potential energy for each charge that gets moved, and the result is that the electric field, the electric potential, and the distance between the two plates are related to each other by V is equal to the negative of E times D. Okay? The negative sign is not terribly important for my present purposes, and it'll just distract us, so I'm going to get rid of it, at least temporarily. Okay? So I'm just going to write it as equal to V is equal to E times D. Okay? I could make this more vigorous if I wanted to, but I don't want to. I don't want to distract us. So we'll just do V equals E times D and not worry about the minus sign for now. Basically, it only is, the negative sign only is related to where you define your zero of electric potential where you're located, so we're not going to worry about it. Now, ICVS, it can be shown, is what that stands for. Maybe I've talked about it in class, maybe I haven't. If I haven't, I'm going to ask you to take my word for it, that the electric field is equal to, this electric field inside here is equal to sigma over epsilon naught. And remember, sigma is the surface charge density, which is the total charge on the plate divided by the area of the plate. Okay? So E is equal to Q over A times epsilon naught. Okay? Remember that sigma is surface charge density. It's the number of coulombs stored on the plate per square meter of area of the plate. Charge per unit area, Q over A. All right, so we have then, putting these together, so V is equal to E times D, but E is equal to Q over A over epsilon naught. So that gives us V is equal to E times D. So Q over A epsilon naught times D. But the capacitance, remember the capacitance is what we're actually after? But I said earlier that capacitance is related to the charge that you store. The amount of charge you can store is equal to C times V. So I can replace Q here with C times V. So V is equal to C times V over A epsilon naught times D. The potential divides out, leaving 1 on this side, and solving for C, which is what we're after, we get C is equal to A epsilon naught over D. Okay. That's the result I was after. And typical values here are A would be like 0.25 I want about a quarter of a centimeter. Yeah, so 0.25 centimeters is what I was trying to go. So that's 0.25 times 10 to the minus 2 meters squared. So that's pretty small. D is typically 1 millimeter. So that's 10 to the minus 3 meters. And then epsilon naught, as you know, is 8.85 times 10 to the minus 12 coulomb squared over Newton meter squared. And then you can substitute that in and calculate the capacitance, which I don't happen to remember. I haven't actually done this calculation, so I'll let you do that at home. It's not going to be a big number. Anyway, that's going to be the capacitance. You calculate that in. But here's a thing I want you to notice, and this will one last point before I end the recording. I mentioned earlier, at least I claimed earlier, that the capacitance of the capacitor was going to depend on how the capacitor was constructed. Well, take a look at what we have in this expression. The capacitance of our parallel plate capacitor depends on what the surface area of each plate is in the form of A, depends on how far apart the two plates are from each other, and depends on epsilon naught, which is just a constant. Okay, and there's nothing in the calculation of capacitance that has anything to do with the battery that you attach to it, or the light bulb that you put in the circuit with it, or anything else. The capacitance is an intrinsic property of the capacitor, which is why, by the way, when I showed you the capacitor earlier, either earlier this recording or previous recording, anyway, I waved the capacitor at you, showed you the stamp label on it. This reason they can label the capacitance of the capacitor without knowing what you're going to do to it or do with it. Okay, so that's capacitance. All right. Charge is not the only thing we store in a capacitor. We also, as it turns out, manage to store potential energy. Next recording will be pretty quick. I'll show you how to calculate how much energy we store when we're storing, as a consequence of storing the charge that we put in. That will be the next exciting chapter in our exciting, oh, never mind. Okay, see you later.